In this video, we will talk about what concavity is. Okay, so to motivate this topic, let's remind ourselves that back in chapter 4, when we talked about derivatives, one of the things that we did was we tried to find where a function f is increasing and decreasing using the derivative. So when the derivative is positive, that's where the function is increasing. And where the derivative is negative, that's where the function is decreasing. So now in this section, section 5.3, we're going to try to get more information about our function, besides the fact that we can find when it's increasing and when it's decreasing. We're going to try to find how f is curving. So not just how it's, whether it's going up or down, but how the graph is curving using, let me space this out a little bit more, how f is curving using the second derivative. And we'll talk about what the second derivative is later in this video. So the notation for the second derivative is I'll write f with 2 primes, that indicates the second derivative, and then x. Okay, so that said, let's give a definition. So if the graph of f lies above all of its tangents, so by tangents I mean tangent lines, we say it is concave up. Concave up. And that's actually the definition of concave up. Okay. So there's a similar definition for concave down, and that's the second part. If the graph of f lies below all of its tangent lines, we say it is concave down. So concave down, and I'm going to abbreviate concave down as CD. I think I might have forgotten to mention this, but concave up, I'm going to abbreviate that as CU. So let's draw a picture of what examples of a concave up and a concave down function would look like to see if we can get a better sense of what the picture would look like. Okay, so I'm going to draw 2 functions. So I'm going to draw a graph here and draw a graph here. So first I'm going to draw a function that looks like this. So kind of parabola-esque. And now in this graph, let's draw some tangent lines. So if I were to look at a point here and draw the tangent line, it would look something like this. If I were to take another point, maybe here, and draw the tangent line, it would look something like this. So it's a little bit more flat. And I think at this point it's not too hard to see that no matter what point I were to take on this graph, if I were to draw the tangent line at that point, the graph of the function is always lying above the tangent lines. So that's concave up. So this graph is concave up. And notice sort of like consistently across the graph, it's sort of curving upwards at all points. Okay, so let me draw another example. Let's say I have a graph that looks like this, curving down, but it never sort of like comes down. It keeps just going up, but just keeps curving like this. So kind of like a log function graph. So let's draw some tangent lines to this graph. So if I were to look at a point maybe here, and draw the tangent line, that would look something like this. All right, tangent line. And let's look at one more point. If I were to look at a point here, further down the road, and draw the tangent line, maybe that would look something like this, something like this. But in this picture, the graph of our function is lying below all of the tangent lines. So this one would be concave down. So this is an example of a concave down function. All right, so now I want to give a memory trick to help us quickly remember what a concave up and a concave down function look like. So memory trick. So the thing to remember is that a concave up function, the graph has an upwards u shape. So by that I mean something like this. It doesn't have to be this whole shape, it could just be part of this shape, so it could be just like this part. That would be a concave upwards portion of a graph, or it could be that whole thing. But an upward sort of U corresponds to a concave up shape. Okay, on the flip side, a concave down graph would have a downwards U shape. So a downwards U. So an upside down U, that would be like this. An upside down U. And it doesn't have to be the whole part of that graph, as we saw in our concave down example. It wasn't the whole part of an upward down U, it was just sort of part of an upward down U. All right, so let's look at an example. Okay, so we have this graph, and what I want to do with this graph is I want to identify sort of on each of these intervals that's separated by these points. So where A is, and where B is, and where C is, D and E, it sort of splits up the x-axis into intervals. And on each interval, I want to specify whether my function is concave up or concave down. So what I want you to do is first pause the video, just for a minute, it should be pretty quick, I think, and try to identify whether it's concave up or concave down on each of these intervals. So 4, 3, 2, 1, pause the video. Pause the video and try this for 1 minute. Alright, so hopefully you've done that. Hopefully you've paused the video for about a minute or so, maybe 2 minutes, because I know maybe part of this time you were copying down the graph, maybe for 2 minutes to try this question. So let's go ahead and talk about it together. So on this first interval to the left of where A is, our graph sort of has this downwards U shape. So it would be concave down here. So I'll write CD for concave down on this interval. So this means concave down. Okay, and then from A to B, it has an upwards U shape. So from A to B, it would be concave up, or I'll write CU. So CU means concave up. And then from B to C, well, it switches back to a downwards U shape. So that would be concave down. So CD, concave down. And then from C to D, it has an upwards U shape. So concave up, concave up. And then from D to E, it's actually concave up again. It has an upwards U shape. So that is also concave up, just a little tiny little sliver there. And then from E onwards, it has a downwards U shape. So that would be concave down. So concave down there. Okay, so this is kind of the basics of concave up and concave down. I want you to recognize, based off of the shape of the graph of an original function, where it's concave up and where it's concave down, depending on does the graph have an upwards U shape or a downwards U shape. So we have a special term that we use to describe points where a function is continuous, but it changes concavity. So that happens, for example, at point A. The function changes from concave down to concave up at that point. So I want to state the definition of that term. Alrighty, so the term is called an inflection point. So we say that a point P on the graph of y equals f of x is an inflection point if, and there's two conditions that we need. So the first one is f needs to be continuous at P. F needs to be continuous at P. And F changes concavity. So what that means is it either changes from concave up to concave down, or from concave down to concave up at P. Okay, so typically when people learn about inflection points, they remember the second condition, that F changes concavity, and that's what makes an inflection point. But the first condition is really important as well. If my function is not continuous there, even if it changes concavity, it's not an inflection point. In fact, so that's important. Let me just leave it at that. We need both of these conditions for it to be an inflection point. So let's go back to our graph and identify the inflection points. Okay, so here is our graph. So the places that this graph might change concavity are these labeled points, A, B, C, D, and E. Those are the places where it may possibly change concavity. And just by looking at my graph, it's continuous at all of them, so I don't need to worry about that continuity condition in this specific example. Okay, so let's label where all the inflection points happen. So an inflection point would happen at a place where the graph is continuous, and it changes concavity. So that happens at A. It changed from concave down to concave up. It happened at B. That changed from concave up to concave down. It also happened at C and at E. But it did not happen at D, because D just stayed from concave up, and on the other side it stayed concave up. So it was the same concavity on both sides. So that's not an inflection point. All right, so next I want to give a key definition that's going to let us help figure out where a function is concave up and concave down. And this is the second derivative of a function. So the second derivative of f, which is written f double prime, that's the way I say this, I say f double prime of x. Or using our other notation, we would write this as d2f dx2. So that's using our Leibniz notation for derivatives. This second notation I'm going to use less frequently. I'll use the prime notation more. Okay, but regardless, we do have those two notations for this. So the second derivative, what is it? What is it actually? It's the derivative of the first derivative. It's the derivative of f prime of x. So in other words, I have to take the derivative twice to get the second derivative. So let's do a quick example. So let's say that we had the function f of x, and it's this polynomial here. Let's find the second derivative. Okay, so to do this, I don't need quotient rule. Even though I see fractions, I don't need quotient rule, because I see the denominator is a constant, the 5 here. So I could rewrite this as 1/5. I can bring that 5 in front as a 1/5. 1/5 x to the 5, and now that's just a power rule. Same thing with the next term. I don't need quotient rule on this, because the 3 on the bottom is just a constant. I could think of this as -8/3 x cubed. And that's useful to do because it's going to save me time. If I did quotient rule, it's not wrong. It's just going to take a little bit more time to do. Okay, so now if I do the derivative, the 5 is going to come down, cancel to 1/5, and we will get x to the 4. With the next term, the 3 is going to cancel with the 3 on the bottom, and I'll get -8x squared. And the derivative of plus 2 is 0, because that's a constant. So now I got to do the second derivative, which means take the derivative one more time. So the derivative of x to the 4 is 4x cubed, and the derivative of -8x squared, bringing that 2 down, is -16x. And that's our second derivative. Alrighty, so now that we know what the second derivative is, there's an important connection between figuring out when a function is concave up and concave down and the sign of the second derivative. Okay, so that I'm going to state a key theorem that establishes that connection. So this theorem, I'm going to call this the concavity test, because it's a test that I'll use to determine when a function is concave up and when it is concave down. So there's two parts to it. So the first part says if f double prime of x is greater than 0, meaning the second derivative is positive, for all x in I, where I is some interval, then f is concave up. F is concave up on that interval. So when the second derivative is positive, my function is concave up. The second condition says when the second derivative is less than 0, when it is negative, then f is concave down. Okay, so the key to determining when a function is concave up and when a function is concave down is looking at the second derivative and figuring out when is it positive and when is it negative. So it's really similar to what we do with the first derivative and figuring out when is the first derivative positive and when is it negative to determine when a function is increasing and decreasing. Now we're just going to be doing that with the second derivative for concavity. So let's do an example. So for the function that we were looking at before, let's determine on what intervals is this function concave up and on what intervals is this function concave down. Okay, so I'm going to break this up into steps, just like we did for increasing, decreasing. So step one is to find where the second derivative equals 0, or the second derivative is undefined. And the reason we do that is those are the only possible points where the second derivative might change sign. From positive to negative, or negative to positive, is when the second derivative equals 0, or when it is undefined. Okay, so let's find the second derivative. So we had already done that, so let's just recall what it was. So the second derivative of this, recall, was equal to 4x cubed minus 16x. Okay, so we need to set that equal to 0. So set 4x cubed minus 16x equal to 0. And we're also going to figure out when it's undefined. So 4x cubed minus 16x, when is this undefined? Well, this is never undefined. There's no value of x I can plug into that to make this undefined, because there's no possible issues that I run into, like dividing by 0, or having like the square root of a negative number or something like that. Okay, so let's figure out when is that second derivative equal to 0 now. I can factor a 4x out of both terms. And when I do that, from the first term, I'm left with x squared. From the next term, I'm left with minus 4. And this equals 0. And now x squared minus 4 is the difference of squares. So that factors. I got 4x. And this becomes x minus 2 times x plus 2. That's using difference of squares. Equals 0. And now that it's factored and it's equal to 0, I can go ahead and say what x is. So from the 4x term, I get x is 0. From x minus 2, I get x is 2. And then from x plus 2, I get x is negative 2. Because I'm setting each of these things equal to 0. All right, so that is step one. Figure out when the second derivative is 0, which happened at 3 points, and when it's undefined, and that didn't happen anywhere here. Okay, so we are on to step 2. So step 2 is to put the points where the second derivative equals 0 or is undefined on a number line and make a sign chart. Make a sign chart of the second derivative. So really similar to what we did for increasing and decreasing with a sign chart for the first derivative, but now we're doing it for second derivative because we're dealing with concavity. Okay, so I'm going to make a number line. So a number line, and every single value I got in step 1, I have to put as a tick mark on this number line. So that's negative 2, that's 0, and that's positive 2. There were no values that made the second derivative undefined, so I don't need to worry about putting any of those on here. And it's helpful to remember what the second derivative was. So the second derivative was 4x times x minus 2 times x plus 2. That's what it was in factored form. And it's helpful to have it in factored form just because it's a little bit easier to plug test points into factored form. Okay, so now let's pick a test point in each interval. So maybe I'll do negative 3 here, and negative 1 here, between 0 and 2. Maybe I'll do positive 1, and then bigger than 2, maybe I'll do x is positive 3. So I need to keep track of the sign of the second derivative now, and then what that means about the original function f. Okay, all right, so I'm going to make a table here for my sign chart. So let's start plugging in these test points into the second derivative. So let's first look at the second derivative and plug in negative 3. So 4 times negative 3 is negative 12. Negative 3 minus 2 is negative 5. And then negative 3 plus 2 is negative 1. So overall, we have a negative times a negative times a negative, which is a negative. Okay, now let's plug in negative 1. So the second derivative evaluated at negative 1, I'm going to get negative 4 times negative 3 times positive 1. So 2 negatives make a positive. So positive here. All right, so next let's plug in 1 into the second derivative. That'll give me 4 times negative 1 times 3. So just one negative number here, which means overall, this is going to be negative. Negative. And now let's plug in 3. So plug in 3 into the second derivative. That gives us 12 times 1 times 5. Okay, that's a positive number, because all of those are just positives that we're multiplying by each other. So positive. Okay, so when the second derivative is positive, that means the original function is concave up. So I'll write CU, concave up. Now let's just draw a picture of a concave up thing. So concave up, draw a picture. And same thing when I plugged in 3. Second derivative is positive, which means original function is concave up. And on the flip side, when the second derivative is negative, that's where the original function is concave down. So I'll write CD, that means concave down. So CD, concave down shape. And then I need to write down my answer. So what are the intervals where this is concave up? And what are the intervals where this is concave down? I'm going to write it down here, but then just transfer my answer onto the next page, because I'm running a little bit low on room here. But I want to write down my answer while I can see my sign chart, just because it's a little bit easier. So F is concave up on 2 intervals from negative 2 to 0, and then one more, so I put a union symbol. The other interval where it's concave up is from 2 to infinity. And now let's write down where it's concave down. Okay, so F is concave down on the interval from negative infinity to negative 2, and then also on the interval from 0 to 2. Okay, that is my answer. So one important thing that I want to note about this is, in this number line, the signs just happen to alternate. Negative, positive, negative, positive. But just like we've seen with the first derivative number lines, they don't always just alternate like this. It's possible to have back-to-back positives or back-to-back negatives. I could even have 3 positives in a row, or 4 positives in a row, or negatives in a row. So we don't want to just pattern recognize and just think, oh yeah, it always alternates. That would be a mistake. Okay. So I'm going to copy this answer and just paste it onto the next page. All right. So now let's do part B of this question. Find the x values of any inflection points of f. Okay, so for inflection points, we're looking for places where the concavity changes and the function is continuous. So it's got to be a place that's where the concavity changes, but also the original function has to be continuous there. So where did the concavity change? Let's look at our sign chart. So it changed at negative 2, concave down to concave up, at 0, from concave up to concave down, and at 2, from concave down to concave up. Okay, so let's write down all of those values. So this just asks for the x values of the inflection points. So that happened at negative 2, 0, and positive 2. Those are the places where the concavity changes, but I still need to check, well, is my original function continuous at these? If my original function is not continuous at these, they're not inflection points. So that's important to remember. So what was our original function? So our original function was this polynomial, and polynomials are continuous everywhere. So let's write that down. So the original function, f, is continuous on, at at all of them, or all of these values, since f is the original function, is a polynomial, and polynomials, I'll just abbreviate polynomials, are continuous everywhere. I'll also abbreviate continuous everywhere. Okay, but it's important to check that condition about continuity. So now we can say what the inflection points are. So the inflection points, now we do know, sorry, the inflection point, I should say inflection point x values. So this question just asks for the x values. If it asks for the inflection points, I should write down the x and the y coordinates together because it's asking for the points. But this problem just wants the x values. So the inflection point x values are -2, 0, and 2. Again, one final time I want to stress that there's two things I need for something to be an inflection point. The concavity's got to change at that point, and the function, original function, needs to be continuous there. And it's important to check both. So in terms of our goals for the section, we have done our first two goals. We've defined what it means for a function to be concave up, concave down, and talked about the relationship between that and the second derivative and its sign. And then we've done an example where we found intervals where a function was concave up and concave down. So the next video, we will talk about what's called a second derivative test. This is going to be another way for us to test whether critical numbers are local mins or local maxes.